Hi, in this video we'll talk about the concept of abstraction and how it relates to program design. To answer the question, what is abstraction, let's take a look at an example. Let's start with the question, how does a driver accelerate a car forward? You could easily respond, well, a driver presses down the accelerator pedal. Great, job is done. The question is answered. A driver of a car now knows how to accelerate it forward. But with that answer, you're leaving out a lot of detail on how that car actually starts moving forward. You could go deeper with an answer like this. A driver presses down the accelerator pedal, generating power in the engine that forces the car's tire to rotate on the pavement. The average driver might not need to know all of this, but it could be helpful for those who are curious. You could take this even a step further, like this. A driver presses down on the accelerator pedal, sending an electric signal to the ECU, which calculates, etc., etc. This seems like way too many details for an average driver of a car to know. It may be relevant for a car engineer, but not for most people. With the top answer, a driver presses down on the accelerator pedal, you have successfully used abstraction to provide enough information to the driver of the car without overwhelming them with too many details. So what is abstraction? Abstraction is the process of reducing complexity by focusing on the main idea. John Guttag, a prominent computer scientist and educator, said, "The essence of abstractions is preserving the information that is relevant in a given context and forgetting information that is irrelevant in that context." By hiding details irrelevant to the question at hand and bringing together only the needed details, abstraction reduces complexity and allows one to focus on higher level applications. Back to our car example. The top level captures the main information relevant to someone who is driving the car. The bottom answer provides too many details for a driver. Abstraction limits the information to what is needed by the driver in order to operate the car. There are two main types of abstraction you will focus on in this course: data abstraction and procedural abstraction. Let's look at another example to better illustrate this. Suppose you are out to dinner and you look at the dessert menu. You see a chocolate souffle on the menu, your favorite. For most people, including yourself, it doesn't really matter what the ingredients are or how it's made. You just know that you like chocolate souffle. Think of the ingredients of the chocolate souffle as its data or its details. Data abstraction says that you just care about the final product, you don't need to know all its data or details. Likewise, a chocolate souffle has a specific process or procedure to make it. Procedural abstraction says that you just want the final product, you don't care about the procedure used to make it. Let's see how these concepts relate to computer science. Data abstraction provides a separation between the abstract properties of a data type and the concrete details of its representation. For example, an integer has a set of properties that are useful to you as a programmer. It can hold positive and negative whole numbers, it has a minimum and maximum value it can hold, and it can use arithmetic operators. But there are also many details that won't matter to you, and those are abstracted away. For example, details about an integer being a 32-bit binary number stored directly in memory in chunks of 8-bit bytes, the concrete details of its representation, don't matter when just using an integer in a program. Data abstraction also manages complexity by giving data a name without referencing the specific details of the representation. For example, when you create int, string, and Boolean variables, you don't need to explicitly dictate what kind of memory storage and addresses are needed for each. Data abstraction takes care of those details to keep it simple for the Java programmer. An attribute is a type of data abstraction that is defined in a class outside any method or constructor. In this case, you have a class variable whose value is shared by the class and all of its instances, and an instance variable whose value is unique to each instance of the class. The constructor is using a parameter to provide a unique name value to each person object created. In both cases, these attributes allow you to represent and manage the data associated with an object without needing to expose the details of how the data is used and stored. In this example, all you need to know is that the person constructor takes one string argument. Beyond that, the details of its implementation can be abstracted away. And finally, data can take the form of simple values or a collection of values. This sort of data abstraction provides you with flexibility in how you choose to structure and manage data in your programs, ranging from simple to complex data representations as needed, as shown here with primitive variables, objects, custom classes, and arrays. While data abstraction is very important, as a programmer, it may not cross your mind often since much of the abstraction is built right into the language itself. In contrast, procedural abstraction is something you'll think about and use frequently as you are developing your programs and working with third-party packages and APIs. Procedural abstraction is all about being able to place the details of an action or procedure into a named method, which you can then use without needing to know any of those details. It allows you to focus on what the action does, not how it does it. It helps with problem decomposition and reducing repetitive code. It facilitates smooth maintenance or modifications without necessarily needing to notify all those who use the shared method. At the highest level, procedural abstraction helps you decompose larger behaviors of a class into more manageable and discrete smaller behaviors. For example, let's say you have a MakeShapes class that is just one long list of code, which can output 3 different shapes. You can use procedural abstraction to decompose your class into methods that create each shape, like this. Already, this makes your code easier to understand and reuse. If you include parameters in these methods as well, like these, you've now created and generalized methods that can be reused with a range of input values or arguments. Procedural abstraction also allows you to ignore the details of an individual algorithm once it's written and tested. Take, for example, this algorithm that determines if a number is a prime number. There are a lot of details here that you don't want to have to remember every time you need to check if a number is prime. So, you stick it in a name method, in this case is prime, and now anytime you want to check if a number is prime, you can just call that method. Easy! No more needing to know those messy details, they've been abstracted away. The algorithm is now easy to reuse without needing to repeat any code. This helps manage the complexity of your program and break down the main flow into distinct, concrete steps. Additionally, if you ever want to improve the algorithm at all, you can do so without impacting the main body of your program. This also means that you don't necessarily need to notify anyone who uses this method since the method's signature and output remain the same, though clear communication and logs of changes is best practice. In summary, at the highest level of abstraction, you can just call a predefined method and have its return value stored in a named variable. You don't care about any details of the algorithm, variable, or the storage processes. If you peel back one layer of abstraction, you might be able to look at the details of the procedure itself. And finally, the lowest level of abstraction would be the machine code, the binary code in zeros and ones that would be impossible for us mere humans to understand. Now it's your turn to put abstraction into practice.